I was thinking about Cauchy sequences and Dedekind cuts. I was curious that while they are fundamentally equivalent, they are not equally popular. While I'm not trying to introduce Cauchy sequences and Dedekind cuts, I will read from Wikipedia just to refresh our memory. A Cauchy sequence is a sequence whose elements become arbitrarily close to each other as the sequence progresses. More precisely, given any small positive distance, all, excluding a finite number, of elements of the sequence are less than that given distance from each other. A Dedekind cut is a partition of the rational numbers into two sets, A and B, such that each element of A is less than every element of B, and A contains no greatest element. The set B may or may not have a smallest element among the rationals. An obvious question is, what makes the cut? How's the cut made? That makes us uneasy. We wonder if something is missing. On the other hand, with Cauchy sequences, we can manually generate sequences, so we're comforted. That is why I believe Cauchy sequences are more popular than Dedekind cuts. But wait a moment, didn't we say that Cauchy sequences and Dedekind cuts are equivalent? If they are equivalent, then could something be missing from Cauchy sequences? Let's investigate a bit further. Remember that we want non-trivial intervals of real numbers to have uncountably many numbers. So we need to be able to construct sequences from arbitrary numbers. Manually generating Cauchy sequences is not adequate. One strategy we could try is to generate all sequences of rational numbers, then select the ones with the Cauchy property. Oh, there's the problem. We have no way to decide if an infinite sequence is Cauchy. For example, if we have a sequence of zeros, we should be able to say that is a Cauchy sequence. But the only reason we know it is all zeros is because I said that it is. In other words, no computation can be a decision procedure for the Cauchy property. Whether we use generators or decision procedures, we need a theory of infinite procedures, just like Dedekind cuts require. That's good because it shows that Cauchy sequences and Dedekind cuts really are equivalent. It's not so good that we need a theory of infinite procedures. Many people have assumed that it is trivial to extend the theory of computation to infinity. It is not. Consider that the theory of computation can serve as a theory of a combinatorial engine. If we try to extend such a theory to infinity, we get a deductive explosion because we cannot deduce every possible induction. If any system can be inconsistent, this one has to be. By the way, that is also the answer to the P versus NP problem. Since we want continuous intervals, Cauchy sequences and Dedekind cuts are both inadequate as definitions for the real numbers. When definitions don't work the way we thought they did, it can indicate that our understanding of the rules that we're using may be wrong. We do not have the connection between discrete and continuous mathematics that we've been taught. I believe that this is the answer to more Millennium Prize problems. Good day.